Today, our topic is triple integrals.
So we have single integral of a function of one variable. Okay, here x go from a to b. And then we do double integral of a function of two variables and integrating over a region.
On the xy plane. Now we have triple integral of a function of three variables, and we integrate over a solid E. The E here is a solid in 3D. The R here is a region on the xy plane. dA is the area element. E here is a solid in 3D. dV is the volume element.
Now, when would I use triple integral? You might think about when do I use it? Why do I need to learn about it, right? Okay. Here are some of the examples that you're going to use it in real life.
An engineer can calculate the mass of a steel beam from its density. The triple integral of the beam's density function over the entire beam gives the beam's mass.
Mechanical engineers must find the center of mass of objects in order to properly move and balance them. Each coordinate of the object's center of mass is calculated using a triple integral involving the density function of the object.
A stadium designer can opt to use a roof that is held up by air pressure. The volume of the air required to fill the stadium interior hold up the inflated portion of the roof can be calculated using a triple integral over the stadium interior dimensions.
Okay, perfect. Good job. All right. Now, so those are some examples that you're going to use triple integral, right? Okay, now that's how it works. So over here we have a rectangular box. There's a B here for box. To describe this box, we can describe this as the set of all points where x goes from A to B, y goes from T to B, and z goes from R to X. Okay. Now, we're going to do an integral over this box. So think about this as actually the domain for the function, okay? It's not. So it is the domain for the function. So in the past, we had the domain of the function is the region on the 2D plane, but now we have the domain for the function here is this rectangular box, okay? So you think about there's a function acting on that. So maybe you can think about it's a density function acting on that. So at each different point, you have different density, and this is the domain for the function. Okay. Now we're going to divide this into m times n times l subboxes. Here is one particular subbox, and each one of this has its value delta v. What is the value for this subbox? Delta x times delta y times delta z, right? We got it. Okay. Now for this subbox here, we can actually try to approximate this using pick a single point in this box. Okay, let's call this point xij. Now think about that point over here. It is this line right here. That is the xijk star, yijk star, zijk star. Remember, there's a function acting on this box, and the function value at this point is going to be the function value will be f acting on this point. So that's the function value on this point. Now, if we use this times the value for the box, we'll approximate the integral of the function over this box, because the function here we consider as a continuous function. So the function value doesn't change much. We can actually use this function value to represent the function value in this box. Okay, and we use that to times the value. That will be an approximation to this. Okay. All right, so now we are going to sum all this up. Now I go from 1 to L, J go from 1 to M, K go from 1 to N. So sum up all those values over here for each box, okay? And this is called a triple Riemann sum. And just like before, we're going to let this Riemann sum and let the index here, we're going to divide those into finer and finer sub-boxes. So we're going to let L, M, and N go to infinity. The limit of the triple Riemann sum is going to become this triple integral, and will be a triple integral over this box. So triple integral over the box, let's call that B. The delta V we're going to replace by dV, and what are we going to put over here is L, M, N go to infinity, and what do we replace this by? Yes, you got it. Okay, so that will be f of x, y, and z. So this is called the triple integral of the function over this box B. Okay, so over the box. So remember, we're doing a function is acting on this box. Okay, and we try to find this triple integral of the function over this box. Okay, think about that. It's a domain for the function, this box. Now, do you guys remember Fubini's theme for double integral, right?
Yeah.
I remember at that time we talk about when you do double integral, a continuous function of a double integral of a continuous function over a region, and at that time we have dx dy or dy dx. The order doesn't matter. Okay, you can switch the order as long as the corresponding upper limit of integration match, right? We have also a similar version for that for triple integral. So over here, we have the triple integral of the function over this box over here, the B. Okay. Then you can put dx, dy, dz. X go from A to B. Okay, let me highlight this. So x go from A to B, and y go from D to D. Okay, the box, right? And z go from R to F. So we can express the triple integral over that box this way, but that's not the only way. Equivalently, you can express this triple integral in another way. This time you can have this, you can integrate with respect to y first. So you can have y here go from D to D, and then z here go from R to F, and then x go from A to B. And there's also other combination you can work on. How many combination you can get? You can have, well, alright, so think about this. You can have dx, dy, dz, right? What else you can have? You can have dx, dz, dy, right? And then you can have what? Dx, dz. And you can have dy, dz, dx. Okay. What else? You can have dz, dx, dy, dz, dy, dx. So you can have all 6 combinations to write this. As long as the upper and lower limit here matches, okay, then they will be equivalent to the triple integral over this box B. So that answered the question. I think I had this question. So what is sometimes with respect to x first, sometimes with respect to y first, which one you do first? Well, if it's integrating over a box, then it really doesn't matter which one first. You can actually switch the order as long as the upper and lower limit here match. Right? And that's called the Fubini thing. Okay? Yeah, Fubini. Alright, so let's look at this example. Okay. in this example, we're going to evaluate this triple integral here over a box B. The B is this rectangular box given by this. So how do we find this triple integral? Right? Let's do it together. So we're going to have this integral. Let's just use the same color here. So think about this. So the function we integrate with is xy d squared. Which one you want to integrate first? Yeah, really doesn't matter, right? Yeah, really doesn't matter. Fubini seems say that it doesn't matter if this is a rectangular box and if this is a continuous function.
You have to switch the function around, right?
You don't need to switch the function around.
Oh,
You just need to switch the corresponding upper and lower limit around. Okay?
Right.
So how about we just go by alphabet order? D, X, C, Y, D, Z, right? X goes from what to what? It's going to be 0 to 1, right? Okay. And Y goes from -1 to 2. And Z goes 0 to 3. You got it. Okay. All right. Okay. And this is just one way to do it. Okay. You can do actually it's a total of 6 combinations to do this. All right. So the box over here is equal to this. So how do you find this triple integral? You're going to do the innermost integral first, right? So we're going to do this one first. And keeping the outside here unchanged. What is antiderivative xyd squared with respect to x? At this time, the x over here is the changing variable, okay? And think about y and z as constant. So if it's a constant, then we're going to bring it outside the integral. So we have yd squared over here. And then we're going to times the antiderivative of x. What's the antiderivative of x? It's going to be x squared over 2. You got it, right? Okay. Now we're going to evaluate this. And remember, x here goes from 0 to 1. Then when you substitute over here, substitute x to be 1, substitute x to be 0, and subtracting, you're going to get this over here, right? You're going to get this one over here. So yd squared over 2. Now, what will be the next step? The next step, we're going to do what? Yes, we're going to do the integral over here, right? And then that will become this. And continue this way, and then we evaluate the outermost integral, and you got this, okay. And finally, the answer here will be 27 over 4. Geometrically, this one here is a function of 3 variables. And integrating over this rectangular box, to visualize that, you actually need to think about 4 dimensions, right? Because the box is already 3 dimensions, and then for this function, it's another dimension. Or sometimes you can think about this function like the density function. So you integrate this density function over the box, right? Then you will get the mass of the box, right? Okay. Yeah, question. Yeah.
Can you convert into polar with 4 dimensions?
Yes, you can convert to polar. We'll get to that. Okay, good question. Okay. All right, so not too bad, right? It is an extension of a double integral, right? And we evaluate the inner integral first, and then work from inside to outside. Now we're going to talk about triple integral over a general bounded region, okay? And this time I will call that E instead of B. B for box. E here is just a general bounded region, okay? Something like that, okay? this region here, well, when I say region, it's actually a solid here, okay? It's a solid in 3D, okay? It is bounded, okay? But it's not a ball, okay? The way that we do this is just like before for the double integral. When we extend from, now when we try to extend from a box to this general region, general solid, we're going to define this capital big F function to be equal to this small f function. Remember the function we integrate with is the small f function acting on this. Okay. So we're going to let the big F function equal to small f function on this solid E. Okay, on this solid E. They're going to agree to each other on this solid. And then we're going to let this big F function equal to, guess what? It's going to be equal to 0, okay? On the region that is outside this solid, but inside the box. Okay, so think about it. You're going to have 0 over 8. So you're going to be 0 on the region that is inside the box, but outside of the solid. Okay. So the function is going to agree with the small f function here, but outside the solid, but inside the box will be 0. Then what happens here is when we do the triple integral of this small f function over this solid and this solid here E, then that's equal to the triple integral of this big F function over this rectangular box B, because the big F function will be equal to 0 outside of the solid but inside the box. And the 0 here is not going to contribute to the integral of the function, right? So these two will be equal. And by doing this, we're able to relate this integral of triple integral of a function over this general region to a triple integral of a function over a rectangular box by doing this. Now, using a similar method, okay. And now we're going to try to focus our attention to continual function. Okay, so the small f function here will just only consider continual function. Okay, now for example, polynomial function, etc. Okay, and we only concern about some simple type of region in some simple type of solid. Okay, so over here I outlined what kind of simple type of solid that I have. Over here, the book here called this type 1 solid. This is a type 2 solid. This is type 3 solid. Okay. Let me go over this with you. So in this solid over here, let's look at the type 1 solid. I'm going to highlight this. Okay. And looks like the D here is bounded above by this surface, right? Okay. And then bounded below by this surface over here. That surface down here. All right. So D here is going to be between this surface and this surface. And the equation for this surface is Z equal to U1 xy, and this is Z equal to U2 xy. Okay. Then the D here bounded by this two surface. Okay. We call that, actually I want to make it easier, like a lot of times say, is it a type 1, type 2, type 3? So I make it a simple name for you to remember. I'm going to call this a D type. So I call this a D type solid. The D is bounded below and above by surfaces. Okay, like that. Now, the second type of solid region, or solid, this time notice what happens here. It is the X, okay? The X is bounded below by the surface over here. Let me make it bigger. By this surface, and bounded above by the surface over here. Oh, can I say below and then? Okay. I would say left and right. Okay. Bounded on the it's not left and right. Bounded on one side by this surface and bounded on the other side by this surface, the X over here. So this is a U1, this is a U2. Okay. So X is bounded by this U1 and U2, the surface of U1 and U2. Then I'm gonna just make it easier to remember. I'm gonna call this X-type solid. X is bounded by U1 and U2. Now let me try to write this out. Okay. So the X over here is going to be greater than or equal to this U1. Or this is a U1 of YZ. And then let them equal to this U2 of YZ. So X is bounded below by this, bounded above by this. Okay. Now for the Z type over here, let me try to make it easier. So the Z over here is going to be greater than equal to what? Yeah, you got it. So it's U1 of XY and let them equal to U2 of XY. Okay, like that. So that's the Z type of solid. This is the X type solid. And similarly, this is, I'm going to call this Y type solid. So the Y over here is bounded by surfaces. So below by what? Okay, by U1 X Z. Okay, it is a function of X and Z, and then bounded above by U2 X Z. Then this is called a Y type solid. Okay, all right, very good. Now, once you know this three types of solid, that's going to help us to set up the triple integral. Okay? Let's focus on the first type of solid. Okay, the type 1 solid. It's also called what type? I just called it. It's a Z type. It's a Z type solid. I call it. Okay, so the triple integral of a function over this solid over here is going to be this. Okay, so a function is acting on the solid. Think about that. Okay, so now we have two situations. Looking at this solid here, this is Z type, right? We're going to project this onto the XY plane. Right? So we're going to project this solid onto XY plane, and you see the region over here is going to be this region over here, right? This region right here. The D over here. Okay. Now, depends on this D over here is what type of plane region. Then we will set up the integral accordingly. Okay. What happens if the D over here, the projection of the solid onto the XY plane, is a type 1 plane region? Do you guys remember? Type 1 plane region? Type 1 plane region is what? It's like this, right? So X is going to go from a constant to a constant, A to B, right? And Y is going to be bounded below by this, bounded above by this. That's called type 1. The type 2 region, type 2 plane region is going to be, Y is going to go from a constant to constant, C to D, and then X is going to be bounded on the left by this, bounded on the right by this. That's the type 2. And for this reason, for the solid, I don't want to go type 1, type 2, type 3, because that is kind of confusing, because for the plane region, you already use type 1 and type 2. So for the other one, I would just say X type, Y type, Z type. Okay. Okay, now suppose the projection of this solid onto the XY plane is a type 1 plane region. Then how do we set up the triple integral? Let's do it together. So we'll have this. Remember the function we integrate with is this function. So let's think about integrate with respect to, forgot a comma. Okay. So integrate with respect to what first? So let's think about integrate with respect to what first? If it's a D-type solid, right? So what is a D-type solid here? The D-type solid here means the D is going to be bounded by two surfaces, right? So bounded below by what? U1. D is not, okay? D is this, you see, the surface over here is actually this surface and this surface, okay? So bounded below by, let me highlight this one more time. So you see that it's bounded below by that surface right there, okay? And then bounded above by this surface over here. Okay, so you have two surfaces right here, this and this. Okay, so bounded below by what? By this U1 xy. Okay, so it's U1 xy, and bounded above by what? U2 xy. So if it's a D-type solid, then you will integrate with respect to dB first. Okay. So we do that first. And then we put the lower limit as U1 xy. Okay. Put the over here. And then up here will be U2 xy. Okay. Now, well, what will be next? This is the projection of this solid onto the xy plane is this region. It is a type 1 region. So now we get to this region. Integrate with respect to what first?
What?
Y first. Yes. Okay, so we're going to do dy. Y go from, okay, and then y go from what to what? You got it. So it's going to be G1x to G2x. Okay, and then finally integrating with respect to what? The x. Okay. The x over here go from what to what? Yes, you got it. So I'm not going to change color. X here go from A to B. So A to B over here. Okay. So that's how you set this up. So if it's a D-type solid over here, so we're going to do this. The innermost integral will be this. Okay, so you will integrate with respect to D first, and then put U1 and U2 here. Okay, right? I did a good job. So you can see actually in this picture, okay, and you see that this is a D-type region. You go from U1 to U2, and then down here, this is actually, and this is the G1, okay, and then G2 will be this, and then you set this up. Now, what happens if this is the type 2 plane region? So how do you do that? Now, remember, the innermost integral is still going to be the same because it's a D-type solid. So we'll have f of x, y, z, and then we'll have dz. We go from u1 to u2. But this time, if it's a type 2 region, plane region, so you're going to integrate with respect to what first? X first. Yes, you got it. Okay. So this time we're going to have dx. X goes from h1, you got it, h1 to h2, right? Okay, got it. All right, and then finally will be the integral with respect to y. Y goes from c to d.
What's that supposed to be? That's supposed to be this one right here? That right here is the
Oh, I missed
shadow. That was shadow?
this one over here. Okay, let's check. This is right. So the first one, no problem. Let's look at the second one. Okay.
No.
Huh?
I'm just asking because so this one right here, right?
Yeah.
That's the shadow at the bottom, right? Type one. What's that right there? That's supposed to be that too. The other one.
It's not for that one.
No,
Okay.
that one's that one. Where you got the arrow at that one, right?
Let's go up and down. This one here, x is actually for that one.
Yeah.
This one, x go from this to this, or you can go y go from this to this. This one can be both. Okay, can be both. Now for this one, look at this picture. This is actually an example of this.
That's what I'm saying. I didn't know which one that matched.
Yeah, this two match.
Right.
This one match with this. This one match with this. So for this one, it's a D-type solid.
Right.
So bounded, the D bounded below by U1, bounded above by U2, and the X bounded on the left by this, bounded on the right by this, like that. So this one here is a D-type, but then this region on the XY plane is a type 2, like that. Okay. All right. So it looks a lot of symbol. Looks like the might be a little complicated, but as soon as you write it down and try to think about that step by step, it's actually not too bad. So just remember, over here is this is. If it's a D-type, then the innermost one will be this. Okay, will be that one. Okay. Now let's try some examples. Okay. Example 2. Okay, let's look at this example. We're trying to evaluate the triple integral of the function c over a solid, and let's call that solid E. Okay, the solid here is E. Okay, where E here is the solid is the tetrahedron bounded by this four plane over here. All right. So tetrahedron, it looks like this. Okay. So now x equals 0 will be the yg plane, so will be that one, x equals 0. And y equals 0 will be the xg plane, so that over here. And then z equal to 0 is the xy plane, so down here. And then this is x plus y plus z equal to 1 is this plane over here. Okay, so let me try to highlight that. So this plane over here, okay, is this x plus y plus z equal to 1. Or another word is this. Okay, that one. Okay. All right, so imagine this plane is going to intersect with the three coordinate plane, right? And then we got this tetrahedron over here. Okay. Now we're trying to evaluate the triple integral over this tetrahedral. Remember, the function that we integrate over this solid is this function c. Okay, d is the function. This is the function of x, y, t. Okay, integrate this function over this solid e. E is the solid. Okay. So how do we do this? Let's try to set this up. Okay. So let's try to get the innermost integral first. Let's think about this tetrahedron here is what type of solid? Is it a X or Y or Z solid? What would be an easy way to think? Huh? D type, yeah. So I heard you just said that is a D type solid. Okay. Yes, the D type solid. The D here is bounded above by this surface over here, right? This surface here is the top, okay? And then bounded below by, what's the bounded below by? Bounded below by Z equal to, let me highlight that. It's going to bounded below by this, right? That is the bottom, the green one, right? So let's write down. So bounded below by this, well, this is the xy plane, so D is equal to 0. So bounded below by 0. And yeah, because this is D equal to 0, right? Okay. And bounded above by what? 1 minus x minus y. Yeah, so bounded above by 1 minus x minus y. Okay, this one. Okay, so you said this is a D type solid. Yes, you got it. Okay, so D type. Okay, so once you have this, let's set up the innermost integral first. Okay, so we'll have the innermost integral. Let's do the innermost first. Will be this integral of, well, the function we integrate with is this function z. Okay, because we just said this, right? So this is the function we integrate with. So the function we integrate with is this z, right? So put it there. And then we're going to do dz. So do dz. D goes from 0 to 1 minus x minus y. Okay. So you got the innermost integral here first. Okay, that's good. Okay. Alright, now let's do the outside. So now we're going to integrate with respect to what? Okay, then you look at the projection of this solid onto, because it's D type, you're going to project to what? Because it's D type, you're going to project onto the XY plane, right? So here is the projection onto the XY plane. Okay. Alright, so now we're going to get, so here is the XY plane, right? Okay. So this one here is better that you can actually be type 1 or type 2 region, right? Either way. But looking at this, if you draw the diagram, if you draw it this way, so that will be a type 1 region, right? If you draw it from below to above, okay? Then you integrate with respect to what first? D, dy, y go from 0 to 1 minus x. And then finally, integrate with respect to x. X go from 0 to 1. Right? So you're able to set up the integral here. Okay. Alright. And then to evaluate this will be this routine, right? Okay. Let's try to do it together, just for one time, okay? Now, let's do this. Let's do a couple steps, okay? You evaluate the innermost integral. What's anti with z with respect to z? Z squared over 2, right? Okay, good. So you have z squared over 2, and this z here go from 0 to 1 minus x minus y, and then here will be dy dx. Now we're going to do the substitution. Okay. If you substitute over here, you will have, so you're going to have 1 minus x minus y, and then square over 2, and then we have dy dx. And then later you're going to do this integral over here, we'll continue, and then later you finish it, okay? Alright, so it's going to be finally the answer over here. We'll do the calculation. The answer over here is going to be 1 over 24. What does this 1 over 24 represent? Morgan, you have a question?
Yeah, I just quickly on the equation projected from the XY plane, essentially the limits of information would change only for x and y. But
Yes.
we could do that, right? We could say it as like if we went from type 2 instead of type 1, and that would just be like 0 to 1 minus 1, and then would be
Yeah. So, okay, good question. Okay. So, right now we regard this plane region here as a type 1, right? This is a type 1. What happens if you regard this a type 2 region, which is the next step? Okay. If we do a type 2 region, how do you set as an integral? Okay, let's do it together. So, the innermost is not going to change as we do the step. So, you still have the integral z dz 0 to 1 minus x minus y. That's the innermost integral. And then this one over here, because this one can also regard as type 2. So you can integrate with respect to x first and then y later. And if you do it that way, so that will be, well, let's draw this. It's going to be this, right? That will be type 2. You draw the arrow from left to right, okay? And you see that the y is going to go from, well, y is go from a constant 0 to 1, right? Y go from 0 to 1. X go from what to what? X go from 0 to y minus, 1 minus 1. 1 minus 1, right? Because for this one over here, if you change that, so that you have x is equal to 1 minus 1, okay? And here, this is x equal to 0. So x over here will go from 0 to 1 minus 1. 0 to 1 minus y. And then you will have this triple integral. The result should be the same. Okay, try that. Okay. So if you regard that as a type 2, then you have this. Okay. All right. Here. Okay. Now let's think about type 2 region, right? Type 2 region is like this. Also, what do we call this? What type? It's an F-type. Yes, you got it. Okay. So I call this the F-type solid. Okay. The X over here is going to be, let me write it down. X is going to be bounded below by U1. yz, bounded above by u2 yz. Okay. All right. So how do you express the triple integral of a function integrate over the x-type solid? Then you just need to figure out the innermost integral first, right? So what will be the innermost integral? So let's write down. Okay. So let's figure out the innermost integral. It will be integral of what? Of the function, right? So let's put the function with respect to what? X first. Okay. X goes from what? U1, yeah. U1 to X go from U1 to U2. Right? Okay. That will be the innermost. Now what about the after you've done this? Then depends on what this region. When you project that onto what kind of plane? If it's an X-type region, you project to which plane? The YZ plane. If it's X-type solid, you project to the YZ plane. Okay? So take away the X, you have YZ. So you're going to project to the YG plane, you get this region D. And for depends on this region D is either type 1 or type 2, then you have different. But for now, we don't know it's type 1 or type 2. So what we do over here is we just put a double integral of the region, okay, of that region D. That region, let's put a D. And then over here, we're going to put dA. Okay, remember, this represents the double integral of this over the region D. Okay, so the first step is to figure out the innermost integral first. Okay, and then later you can figure out what to put here and here. You guys got it? Okay, good. All right, now type 3 region. Okay, it's also called a type. Y type. Okay, I call it Y type. Okay, just make it easy to remember. Okay, so the Y over here is going to be bounded by bounded below, bounded above, bounded below by U1 XD, and bounded above by U2 XD. Now, when you evaluate the triple integral of this function over the solid V, okay, then you just need to figure out the innermost integral first. Okay, so what will be the innermost? Okay, let me put it down. Okay, the innermost integral here will be just the function. And you just said dy. Yeah, you got it, dy. Y go from U1 to U2. And then depends on the projection of the solid onto what plane? XD plane, because you take away Y, so you have X and D, XD plane. Depends on this region is what type of region, then we separate. Then we have to think about what to do. But for now, then we can just put double integral over that region, D. Okay, and then here we put dA. Okay, so you can figure out that one. Okay, got it? Okay, good. Not too bad, isn't it? Okay. You can take a break. Okay, take a break and come back in 10 minutes. So let's get this one done. Okay. Right. Example 3. We're trying to evaluate this triple integral where E is this region bounded by this paraboloid and the plane y equal to 4. Okay. So here's the picture. This is the paraboloid y equal to x squared plus d squared. So that's the paraboloid. And the plane y equal to 4 will be this one over here. Let me highlight this for you. So y equal to 4. There's this string over here. That is y equal to, I should use a different color because I use orange. There's this one over here. So that's for y equal to 4. Okay. And then this one here is this. This is right here. Right? Okay. That's the parabola over here. Okay, so we can regard this as a d-type solid. So if I regard this as a d-type solid, how do you think about it? Okay. So if you regard this as a d-type solid, then d is going to be bounded above. I'm going to take this one. So I'm going to actually do this again. Okay, so if we regard this as a d-type solid over here, then the d is bounded above and below, right, by u1 and u2. So here, then the d bounded below by this one over here. That's half a surface. Okay, by this surface below, okay. And then bounded above by this surface over here, okay, like that. Okay, so G bounded below by the blue surface here, bounded above by this surface over here. So we can regard it as a d-type solid. Okay, so let's write down this solid here, the E. Okay, if I regard it as a d-type solid, how would you like to write this? Then we're gonna have D go from D. It's going to be bounded below by what? Bounded above by what? Bounded below. Okay, let's try to think about this one. So down over here, well right here, the surface y equals x squared plus d squared, right? Let's solve for z. So d squared is equal to y minus x squared, right? Take the square root. So z is equal to plus or minus square root of y minus x squared. Now the one above, this one above is going to be d equal to, this one above is going to be d equal to the positive square root of y minus x squared. This one below is going to be the negative square root of y minus x squared. Okay, do you see it this way? Right? So z is going to be bounded below by, yes, it's negative square root of y minus x squared, and bounded above by positive square root of y minus x squared. Okay, so we got that one. Okay, and then we can think about, now if we got it as d-type, then we can project this onto the xy plane. Okay, project onto xy plane. Over here, we got this region on the xy plane. Okay, so we project onto the xy plane. So we got this. So, what kind of region you can think about this? What's the best? Okay, George. Draw the arrow like this. Type 1 or type 2? Type 1, right? So, then type 1, over here, y is going to be bounded by what and what? bounded by, yeah, let's take a look. It's going to be x squared, right? So the x squared here, and x squared over here, and then bounded above by the 4, right? So y is going to bound below by x squared, bounded above by the 4. Okay. Okay, and then finally, x going from what to what? Yes, you got it. It's negative 2 to 2. Okay, because y equals 4, x has to be equal to positive negative 2. So x goes from negative 2 to 2. Okay. So that's the region. That's the region E. Now we're going to integrate the function, which is the function given was this function over the solid. Okay, let's write down. So it will be, well, we put the innermost function integral first. So the innermost integral will be integral of this function, and then b what? dz. D goes from negative square root of y minus x squared to positive square root of y minus x squared. So that's the innermost integral. And now we put the rest. So that is a type of region. So we're going to go integrate with respect to y, right? Y goes from you can ride a motorcycle like that. Oh, we have this on this one. All right. Okay. So y goes from x squared to 4, and then finally x go from what to what? Negative 2 to 2, right? Okay. We do this. Okay. Now to evaluate this integral over here, okay, let's think about this. All right. Now to evaluate this integral over here, okay, let's just do the first step. Okay. Let's actually show this a little bit. So there's some space. What's happening over there? Got it. Is it hard to people say? Back in. Okay. All right. Right down. Okay. So to evaluate this integral, just do the first step, okay? So we're gonna get what? That's going to be equal to. Okay. What is this integral? Let's do the innermost integral right here. Okay. What do you get over here? Wait. Yeah. We do that. So we'll get this to this. This integral is correct, right? Okay. However, let me tell you, this integral is extremely difficult to evaluate. Can you see? It looks very innocent, right? However, it's actually extremely difficult to evaluate. Okay, trust me. If you can fight through this, let me know how you did it. Okay. So, well, it is correct, right? Yeah. It is correct. However, it's extremely difficult to evaluate. Okay, correct. But extremely difficult to evaluate. Okay. So we're not going to do this one. Instead, let's think about an alternative way to do this, right? Okay. What's an alternative way to do this? You can regard this as a Y-type solid. Can you can you regard it as a Y-type solid, right? Y bounded by U1 and U2, right? So Y is going to be bounded by, on the left, by this surface, and then bounded on the right by this surface, orange, by this surface over here. Okay, so left is a yellow surface, and on the right by this red surface over here. That will be, we can think about that as a Y-type solid, right? Okay. So let's write that. So Y is going to be, actually, so Y is bounded below by what? Yes, x squared plus b squared. And then bounded on the right, above, right, on the right, by what? Yeah, this one here is Y equals to 4. So bounded on the right by 4. So right here. Okay, you got that one. Okay. Now, because this is D-type solid, we're going to project onto the XD plane. Okay? And this one here, you can regard this region either type 1 or type 2. However, it's a circular shape, so maybe it's better that we use what? Polar coordinates, right? In polar coordinate, this will be a polar rectangle, right? With a circular region, right? Okay. So let's try to let's write down this triple integral of this function over the solid and put the innermost integral first. So the innermost integral will be integral of the functions that were given, and then dy, right? Because y go from what? X squared plus b squared, and then to 4. So that will be the innermost one, right? So you got this one first. But then for the rest over here, what I was going to do is going to be integrating over the region, right? This region over here is the D, that region D, okay? This region D over here, okay? And then I'm going to put dA over here. Yeah. Then use a different sign. So D over here, dA over here. Okay. So it is better that I didn't finish writing out the solid here because I decided to use the polar because it's easier to use polar. The reason that we are going to use polar is because the shape of this region, okay? It's a circular region, so we use polar, okay? So I'm not going to bother to finish this part right here. So I just put integrating over this region in dA. Now let's finish this. So that's equal to set up the region, okay? This part over here will be the sum. How about we try to evaluate that? How about we try to evaluate this innermost integral? What's untitled with this with respect to y? It will be that times y, right? Because this doesn't have contain y. So untitled with this will be this times y. So we should have square root of x squared plus y, x squared plus b squared. And then we will have the y over here. And then y goes from x squared plus b squared times 4. Actually, because this is kind of like a constant with respect to y, so it will be 4 subtracting this times this. Okay? So That was the innermost integral. Okay, and then I will put dA here and integrate over the region C. Okay. Let's try to get this done. Okay, how do we do this? I'm going to change to polar coordinate. Okay, so I'm going to use polar coordinate. In polar coordinate, looking at this one right here, right? This is on xg plane. So x squared plus z squared will be equal to what? It's r squared, right? So remember, in polar coordinate here, x is equal to r cosine beta, y equal to, sorry, it's not y, it's d. D equal to r sine beta, and then x squared plus y squared, x squared plus d squared equal to r squared. So now x squared plus g squared here, you're going to replace by r squared, right? And this one here is this what? This is r, okay? Let's do that. So we're going to have r times 4 minus r squared. Okay, what do you replace the dA here by? dA by what? R dr d beta, right? So we have R dr d beta. R go from what to what? Let's take a look here. R go from 0 to, what's the radius for this circle? 2. So R go from 0 to 2. And what about data? Data go from 0 to 2 pi. You got it. Okay, 0 to 2 pi. Now this will be a simple integral, right? You know how to evaluate. Okay. So you just need to multiply this in and find antiderivative, etc. And finally, the answer here should be equal to 128 pi over 15. Okay, and I know that you guys can do the algebra, do the calculation right here, right? Good. Alright, so okay, I'm not going to do the animation, but I have a couple remarks to make. Okay, so remark over here is the limit integration in the innermost integral. Okay, like that one. Look at the upper and lower limit. Okay, they contain at most how many variables? Two variables. Yes, you got it. Okay, so two variables. Okay, and then what about the middle? The middle integral contains at most one variable, and the limit of integration in the outermost integral contain no variable. It must be what? Constant. Okay, good. You got it. Okay. All right. So two variables at most, one variable at most, constant here for this outer integral. Okay. Now application of triple integral. Remember, for function over here is a positive function. The single integral of the function from a to b, what does it represent? It represents the area under the curve, right? Okay, if it's a continuous function, that's the area under this curve from a to b. Okay? What about this double integral here of this function over region C? What does it represent if it's a positive function f? Represent the variance, okay? Yeah, looking at the graph of this, okay? So actually represent the variance under the surface, okay? Under the surface over here, okay? And over this region D. So that's the value under the surface and above the region D. Now today, we have a triple integral over a solid V. In order to think about this, you have to have actually 4 dimensions. And this one here represents the actually represent a hypervolume of a four-dimensional object. Okay, so this is a volume, this is a hypervolume. So one more dimension. But for you guys, I will suggest that you think about this function here, maybe like a density function or temperature function. So you just need to add one more dimension to that. So think about either the density or the temperature, okay, for every point in the solid. Okay. So I couldn't have a picture here because it requires 4 dimensions. So it's a hypervolume of a 4-dimensional object. Now let's try to think about this simple case here. If it's the integral of 1 from a to b, then what do you get? You get b minus a, right? Okay. And what does it represent? Represent the length of this interval, a to b, right? It's the length of the interval. What happens if you integrate 1 over region d? What do you get? Well, think about that. This region over here is d, and this function here is 1. So integrate 1 over the region d. The value of this is going to be base area times height. So it's the base area of d. It will be this area of d times the height 1. In numbers, that will be the same as the area of the d. So this one over here will be equal to the area of d. What happens if you integrate 1 over a solid E? What do you get? Yes, you got it. Okay. So it's the value of this solid E. Think about the one here as a density function.
Then this integral here is equal to 1 times the volume. So that's the same as the volume.